This is Phil Koopman with an overview of embedded software testing. We'll start with a quote from 1962 when a rocket was lost because a single hyphen had been left out of an instruction tape. The point being made is that even the smallest of errors can cause a catastrophic problem with your software. Therefore, testing is a very difficult challenge. Generally, the best you can hope to do is to find a lot of the high-value bugs. Probably testing isn't going to find all the bugs. Nonetheless, we should try as hard as we can to have a thorough, methodical way of ensuring we get appropriate testing coverage within the budget available. For this presentation, we're going to be talking about the right-hand side of the V, having to do with all the different types of testing that need to get done to ensure software quality. Testing in general is a way to execute software. So if you're doing things that don't actually involve a program counter going down a program, it's not really testing, it's some other form of validation. In testing, you have a piece of software under test, and a workload is applied to it to measure the actual behavior of the software while it's running under a particular workload. An oracle generates expected results, so that means you have something that isn't the software telling you for a given workload, what do we expect to see out the other side of the software. You then compare the actual behavior to the expected result, and the test passes if they match and fails if they don't. Note that this can be a little tricky because sometimes the expected behavior of a software is something unusual, such as the software terminating when you tell it to shut down, and the test passes if it's supposed to shut down and it actually shuts down, or if a process dies under a kill command and it's actually supposed to die. So it isn't about whether the software does something that you think seems reasonable. It's simply about whether the software under test does what it's supposed to do according to an oracle that predicts the correct behavior. Some anti-patterns for testing are when you see primarily ad hoc informal testing, people just beating on software to see what happens. That's probably not good testing, especially if that's the bulk of the effort. If you have no defined notion of test coverage, that's also a problem. Test coverage has to do with the question of, well, did we do enough testing? We'll talk about that more later. If there's no defined pass, test, fail criteria, that's also a problem. If you don't have an oracle and you're not matching the actual behavior against an oracle, that's a problem. And here again, we have people just beating on software to see what happens. That's not testing if you don't have an expectation of what the right answer is supposed to be. Testing in general is a way to execute software. So if you're doing things that don't actually involve a program counter going down a program, it's not really testing, it's some other form of validation. In testing, you have a piece of software under test, and a workload is applied to it to measure the actual behavior of the software while it's running under a particular workload. An oracle generates expected results, so that means you have something that isn't the software telling you for a given workload, what do we expect to see out the other side of the software. You then compare the actual behavior to the expected result, and the test passes if they match and fails if they don't. Note that this can be a little tricky because sometimes the expected behavior of a software is something unusual, such as the software terminating when you tell it to shut down, and the test passes if it's supposed to shut down and it actually shuts down, or if a process dies under a kill command and it's actually supposed to die. So it isn't about whether the software does something that you think seems reasonable. It's simply about whether the software under test does what it's supposed to do according to an oracle that predicts the correct behavior. Some anti-patterns for testing are when you see primarily ad hoc informal testing, people just beating on software to see what happens. That's probably not good testing, especially if that's the bulk of the effort. If you have no defined notion of test coverage, that's also a problem. Test coverage has to do with the question of, well, did we do enough testing? We'll talk about that more later. If there's no defined pass, test, fail criteria, that's also a problem. If you don't have an oracle and you're not matching the actual behavior against an oracle, that's a problem. And here again, we have people just beating on software to see what happens. That's not testing if you don't have an expectation of what the right answer is supposed to be. In contrast to the unstructured testing approaches are the methodical testing approaches, which we'll call black box and white box testing. Black box testing involves using the requirements to guide test design and exercising all the code functions as based on the requirements and functionality of the system. It's called black box because you're not supposed to look at what's inside the software. You're supposed to just know what the functionality is, and the inside of what's inside the software is a mystery, in other words, a black box. In comparison, white box testing starts with the source code and works backwards, saying, I see the structure of the code. Let me make sure that my tests are designed in order to exercise all the code. And typically the objective is to hit all the paths through the code. So it's called white box, or some people call it clear box because you can see inside, but the preferred terminology is white box testing. In order to get thorough coverage, you need both black box and white box testing. Black box testing can miss implementation corner cases. So if you have just the functionality test, there might be some special value that you didn't know was special that causes the code to crash. And with black box testing, it's really hard to know what that is. In contrast, white box testing doesn't exercise missing functionality. So if you have a missing if statement inside the code, you don't know to test it because it's not there. But the requirements might say, well, there's a special case and the if is supposed to be there, but it's not. The notion of coverage varies depending on your test strategy. For white box coverage, usually you say my code coverage is a fraction of the code exercised in test. For example, you might say I've been able to exercise 97% of the lines of code in my system. That's my code coverage. Black box testing also has code coverage, but it's measured differently. It's going to be measured on the fraction of requirements exercised. So I have 73 requirements and I only exercise 72. Well, that's 72 out of 73 black box coverage, which is completely independent of how many lines of code were tested. So it's important to realize, while some people think or say code coverage is only about how many lines and what fraction of lines, in fact, coverage depends on what type of test you're running. And for black box, it's about the requirements coverage, not the code coverage. There are other types of coverage depending on testing. For example, you might say the fraction of state chart arcs covered or things like that. And we'll get into that as we talk about other types of testing. While there are different approaches to testing that result in different notions of coverage, there are also different times at which you test within the V process. Unit testing, down at the bottom center of the V, typically involves executing tests against a single code module, doing subroutine tests with various inputs. These can be very extensive and get very high white box test coverage. At the next level up is integration test, which is more about do modules play nice with each other, and that can be some combination of white box and black box testing. Up higher is software test, where you're exercising at the system level all the software functions of a system or subsystem, and that tends to be much more black box about did you actually hit all the requirements. At the top right of the V is acceptance test, which has to do with whole products tests of both hardware and software together, mostly looking at customer use scenarios, and those are generally almost entirely black box tests. But you also typically see some smoke tests and some exploratory testing just to make sure that the requirements seem to be complete and accurate in terms of customer usage scenarios. There are other places where testing show up, and they have their own uses. Beta test, for example, is supposed to see if representative users discover defects. Now, this test gets abused. A lot of times people take software which may not be fully baked, and they sell it to people and they say, well, we'll just call it beta, and that way people know it's not 100%, and then they send it to the public. And that can lead to problems with your public perception of your company. Strictly speaking, beta testing should not be a full-scale public release, but rather should be released to just a few trusted customers who have reasonable expectations and are going to be very diligent in reporting bugs back to you. Regression testing is an approach to testing to see if a previously fixed bug comes back. So this means that every time you fix a bug, you create a test to make sure that bug was actually fixed, and then you run it every time you touch the software to make sure that a previously known bug didn't come back to bite you. Performance testing isn't really about functional correctness, but rather about the ability of the system to handle a high workload and to identify performance bottlenecks. So in this case, the Oracle isn't really looking for correct answers. Well, you hope they're correct. It's much more interested in how long things take to run and whether you have some sort of computational bottleneck. Robustness testing has to do with what happens when you get invalid inputs to the system. While the invalid inputs might result in undefined behavior, Generally, it's a bad idea if that undefined behavior causes an entire system crash or some dangerous output. So typically with robustness testing, you see some exceptional inputs being put in, and the oracle is something straightforward, such as the system doesn't crash, the system doesn't hang, or the system does not violate its safety requirements. Security testing has to do with whether there are vulnerabilities that an attacker can use to penetrate the system. And again, there, it's often more about exceptional inputs and strange things the system was not designed to handle, and seeing whether attackers can use those vulnerabilities to get a toehold in the system. Finally, fault injection, which is related to robustness and security testing, involves simulating component failures or flipping bits in memory or otherwise simulating what happens when something goes wrong. And again, the measure of test success is often not did it work perfectly, but rather did it behave in a reasonable manner, and did it especially not do something unsafe, even though a reasonably expected fault actually occurred. Perhaps surprisingly, even though we know what testing does, there are completely different motivations for testing depending on what kind of software quality you expect. We all know that the point of testing is to try and find bugs. But the question is, why are you trying to find the bugs, and what do you do once you find a bug? For testing low-quality software, which includes possibly everyday IT quality software, where if it doesn't work every single time, it's probably okay as long as it works most of the time, the point of testing is really, it sounds like debugging. You test, you find a bug, you remove a bug, and you keep going until you run out of time because there always seems to be one more bug. The question is, how many bugs are left after this? Let's say you have 100,000 lines of software and you run some tests and you remove 10,000 bugs and you're done testing and you can't find any more bugs with your tests. How many bugs are left? Well, you don't really know because probably your tests missed some things, but it's really a bad bet to say there are 0 after 10,000 bugs. Probably didn't catch them all. Now again, this may be okay for everyday quality software, but that software is going to have some bugs in it, and you're just going to have to live with that. In contrast, if you're building a life-critical system where someone could die if your software doesn't work, you don't want to be out there testing, removing bugs, and just sort of giving up when you can't find anything, because you really have no assurance that the remaining software actually has a sufficiently low number of bugs to be considered safe, preferably 0. Instead, when you're testing safety-critical software, you take a completely different view. The purpose of testing is not to find and remove bugs. It's not about debugging. Rather, the purpose of testing is a quality check on all the design processes you used. You hope that all bugs have been removed via peer review, unit test, integration test, and all those other things. So by the time you get to system testing, you should not be finding any bugs at all. The system test is to prove the hypothesis that the software is basically perfect. Product level tests in a high critical or high dependability embedded system should never find a software bug. If you find a bug, it doesn't just mean, oh, there's a bug, let's fix it. It means that somehow this bug made it through all these different verification and validation procedures to the point where something must be broken in your process. So when you're testing safety critical software and you find a bug, yeah, sure, fix the bug, but that's actually not the point. The point is, how come you didn't find that bug in peer review? How come you didn't find that bug in unit test? How did that bug slip through? And so when you're testing safety critical software, you treat finding a bug in product test as an all-hands emergency that your process is broken and you need a big fix to make sure that all the other bugs that must have slipped through also got taken care of. That's in stark contrast to everyday software where testing is basically debugging. Embedded software testing best practices revolve around getting the right amount of testing coverage depending on the needs of your system. Getting high testing coverage for white box means you must exercise most or all of the code paths in your software. For black box, it means you have to exercise all the requirements. And as we mentioned earlier, both white box and black box are required because each type of testing has its own type of blind spot. Maybe there's some code that isn't there and the white box test doesn't know how to test it, and maybe the black box test doesn't know how to get into the deep corners to get the edge cases inside your actual implementation. Exploratory testing is valuable and useful to reduce risk, especially if there's unexpected functionality or there's some low-hanging fruit for buggy software. Exploratory testing should be a few percent, maybe 5 or 10% of your test budget, because the white box and black box testing should do the heavy lifting, and exploratory testing should be there to explore edge cases that the white box and black box testers didn't think about, or to take a look for low-hanging fruit of buggy software. Other types of testing can be appropriate, but it all depends on your process, the application, and the type of software you're testing. There are a number of testing pitfalls, and the big testing pitfall is that there are too many timing and sequencing combinations, failure types, and operational scenarios for you to ever get perfect coverage. It's just not going to happen. And if you don't believe that, here, let's take a look at an example. Let's say you have a procedure that takes 3 32-bit integers. And the question is, how many tests to test that procedure? Well, let's assume that there's no internal state, so there's no static variables. It's just a pure combinational function of 3 32-bit values. That is 2 to the 3 times 32 power number of possible inputs, because you have 96 bits and each bit could be some different value, so you need to do all the combinations. That's around 8 times 10 to the 28th input values. Now that sounds like a big number. Well, let's try and make it a little more concrete. Let's assume you can do 1 trillion tests per second, so that's a lot of CPUs going on this testing, and you try and do every single possible integer with 96 bits in it to try and do that test. Well, it turns out if you do the math, that's about 8 times the age of the universe. So even this simple function cannot be completely tested. And so that should give you an idea that when you're testing, you're sampling, you're using heuristics, you're hoping to find stuff. But the hard fact is there's always a combination of inputs you haven't tested, and so you're trying to get different metrics of coverage rather than complete testing for all but the simplest function. Another testing pitfall is that creating an oracle, the test oracle problem, is the hard part. It's okay to have a person doing exploratory testing with a model in their head, but that doesn't scale because you need a lot of people if you want to run a lot of tests. And so you end up having to have pretty good requirements because the requirements drive what the test results should be, and that's how you build your oracle. But this is a known hard problem. It's expensive to build the oracle, even if you can automate the testing. Another pitfall is 100% coverage is not 100% tested. This sort of falls out of the earlier point that you can't test all possibilities. Sure, you can hit every line of code, but you can't hit every line of code with every potential value. And so the coverage is a heuristic, and high coverage numbers are good, but that's a starting point, not an ending point. Similarly, 100% passing tests is not 100% bug-free because you're testing only partially exercise the software. And eventually, if you remove all the bugs you find, eventually you're doomed to pass 100% of your tests. That doesn't mean that you've fixed all the bugs in the system. That means you've fixed all the bugs that you know how to find. And so it's important to do testing. It's important to get high coverage. But in the end, have some respect for the fact that if you found a lot of bugs in testing, that predicts there's probably a lot of bugs you didn't find. Ideally, as we talked about in the philosophy slide, you want to find very, very few defects in the very last pass of testing to give you a warm, fuzzy feeling that probably you caught most or possibly even all the bugs before that last phase.